Alright, hello everybody. Sorry about the background noise, I gotta have my office door open here. So we're looking at our first sub O of n squared sorting algorithm here, and this is Mergesort. So it runs in n log of n time here. And what's more, it is provably optimal, meaning that it does the minimum number of comparisons. It follows the sort of sorting decision tree that we drew in the sort of proof of n log n video. It follows that decision tree exactly. Now, the downside to Mergesort is that normally you can't run it in place. It requires O of n sort of extra memory off to the side as like scratch space to kind of do the sorting in there like that. So that's our sort of trade-off for that optimality is the extra memory usage. But we'll see that there is a situation in which we can actually not have that sort of extra space there. Okay. So as the name suggests, Mergesort is built on a merge operation. So merge takes two already sorted sequences and then merges them into a new sorted sequence containing all the stuff from the original one, but sorted, right? So for the way that this is going to work here, we're not actually dealing with two sequences that are already sorted. They're just two halves of like an array or something like that here. So like here we've got an array. Its left half is sorted in ascending order, right? This goes -1, 3, 5, and 8. And then its right half is sorted in ascending order, 1, 2, 6, 7. So the merge operation kind of threads those two things together and gives me a whole array that is sorted in ascending order there. So how's that work? How are we going to accomplish this here? So the idea is we need to keep track of where we are in the output array. So at least we need an index k into the output array there like that, right? And then we want to say like, well, what should go here? Like what should go at index 0 in the output array? So like if you remember from selection sort, it should be the smallest thing in the input array here. But our input array has this structure to it that means we only have to choose between two things. It could be either this or this. Like the smallest thing in the left half is of course at the beginning of there, and the smallest thing in the right half is at the beginning of the right half there. So I don't have to do like a whole loop to find the smallest thing, I'm just comparing two things at a time. -1 is smaller than 1, so we're going to keep track of where are we in the left half, where are we in the right half, and then grab the smaller of those two things and copy it to the output. So -1 is smaller than 1, so we're going to copy the -1 down there, and then we increment I. I is going to move over here because we used up the -1. Right? In the next one, now we're comparing this 3 with this 1. 1 is smaller than 3, so we're going to copy the 1 down there, and then we're going to increment J to move on to the next one. And so forth, right? So 2 is smaller than 3, so we copy the 2 from J's side. 3 is smaller than 6. Look at where I and J are, right? 3 is smaller than 6, so we copy the 3 to the output. 5 is smaller than 6, so we copy the 5 to the output. Notice that we don't just like, alternate, right? Sometimes we grab more than one thing from the same side in a row there, the 3 and the 5. 6 is smaller than 8, so the 6 goes next. 7 is smaller than 8, so then the 7 goes after that. And then when either I crosses over the green line or J ends up out there past the end of the array, that means one of the two sides is done. So the J side is finished, right? I've transferred everything from J's side to the output there like that. There will always be at least one thing left over on the other side because we only ever increment I or J. We never increment both at the same time here. So then we just transfer whatever that last element is, or if there's more than one, we transfer all the remaining elements into the output array there. There's no merging being done because there's nothing for 8 to compare to, right? I've run out of stuff over here on the right-hand side there like that. So notice that we did that with just one pass over the output array there. Like I didn't have to loop and go backwards or anything like that. So this is going to run in O of n time. So the code for this is like, it doesn't quite fit on one slide, unfortunately, but we have an index I into the left half, an index J into the right half, and an index K into the output. So the core of this is this loop right here. This is where we are merging the two halves together there. So as long as I is still in the right half, and I is still in the left half, and J is still in the right half here, we have two elements we're going to compare. So we compare left with right. If the left half is less than the right half, then we're going to copy the left half into the output and increment I. Otherwise, we're going to copy the right half into the output and increment j, and then regardless, we always increment k. When this loop here is done, that means we've finished the merge part, but there's still probably at least one thing left over on the other side here. So if I get over here, right, this is following that main loop, I know that either I is equal to size over 2, but that means that j is less than size. In other words, there's still one thing left over on j's side there. Or I know that j is equal to size, but that means I know that I is still less than size over 2. So either there's something left on j's side, or there's something left on i's side. Never both, right? We never have like stuff left over on both sides, because then we would have merged it already in the other loop here. So this loop here is going to copy any remaining elements from the left-hand side, and this loop here is going to copy any remaining elements from the right-hand side there. Note that, like, even though there's two loops over here, we only ever run one of them, right? Like, one of these two loop conditions is always going to be false, so one of the loops will be skipped, and one of them will be run there like that. If you sort of like maybe over apply the ternary operator along with some post increments here, you can squish this down to where it all fits in sort of like one thing here. I don't know, this isn't, if this is simpler or like easier to understand, I don't think so. It's not any faster or slower or anything, right? It doesn't change like the big O complexity. The only advantage to this is it fits on like one slide, I guess, like that, right? So this is using the ternary operator to choose which of the sort of two things to copy into the output there like that. This is just mentioning what I was saying, right, is that those two loops at the end here, only one of them ever actually runs, right? It's not possible for us to end the sort of main loop there with both I less than size over 2 and j less than size here. So when we exit the main loop here, we either have I equal to size over 2 or j equal to size. So one of those two loops conditions is always going to be false when we get there. To analyze this here, it's a little bit tricky because we have like the three loops like one after another, right? Should be obvious that like we couldn't do more than like big O of n work here, but we can actually simplify it down for the purpose of analysis by noticing when do we copy in I to the output versus when do we copy in j to the output here. So we copy from the left-hand side, from in I into out there, if I is less than size over 2 and j is less than size over 2, and in I is less than in j. So that's like if we're in the main loop there, right? That's the main loop, the first part of the if there like that. On the other hand, if the main loop is finished, but in I is still less than size over 2, then that means we're in that sort of like secondary loop at the end there. Right? That's where we're just copying stuff from I's side straight into the output there. And then going the other way, right? If I is less than size over 2 and j is less than size, but in I is greater than or equal to in I, that's coming from the main loop. That's when we would copy j's side to the output, copy in j to the output. Or if we've reached the end of the left-hand side here, but j is not yet sort of done there like that. So that would be that third loop there. So the idea is we can kind of smash all this together into one big if-else-if inside of the loop and then eliminate the two extra loops here. So in here we're saying what are all the situations where we copy from the left-hand side to the output? And those are either if we're doing the main loop and the comparison is true, or if the main loop is done and we're doing the second loop there like that. And then likewise, this one over here is what are all the situations where we copy from the right-hand side to the output. And it's just basically the opposite of that here. So the nice thing about this form is it's just one loop driven by incrementing k, right, like that. So it's pretty obvious that this loop runs n times and all the stuff inside of it is just like constant time there, so it's just like nicely O of n there. So this is equivalent to the other one, it just makes it a little bit easier to kind of analyze like the runtime of it there. Okay, so we've got a merge function. You give it two already sorted sequences and it can turn them into a bigger sorted sequence, right? It doesn't run in place. If you want to make an in-place merge, that runs in O of n squared time, which is like, you know, already kind of worse than the other sorting algorithms that we already have there. So that's kind of like not, like, there's no point in doing that. So where do we get these already sorted sequences come from? Like, what's the point in, like, okay, if you give me things that are already sorted, I can sort them. Like, what's the deal with that? Well, so the trick is that the already sorted sequences are smaller than the thing that we want. So we can just recursively use merge sort to create the two halves. So the merge sort algorithm is just, okay, recursively sort the left half. So that gives me, like, if my whole sequence looks like this, right? That gives me an ascending half over there. Then recursively sort the right half. That gives me an ascending thing over there. And then merge them together, which gives me one big thing that is sorting ascending throughout the whole thing there, like that. So this here is the entire merge sort function, right? If our size is 0, we don't have to do anything, right? How do you sort 0 things? You just don't. Now, if our size is 1, how do you sort one thing? You don't. But remember that merge sort is a not in place sorting algorithm. In other words, it copies from in into out here. So even if my size is 1, I still have to do something. I have to copy the one input element into the output there, like that. And this is really setting things up for the recursive merge sorts down here to kind of do their thing here. So then if my size is 2 or greater, right, that's where the if, the else applies here, is if we're greater than or equal to 2. We're going to find the midpoint. What's the middle point of this whole thing here? We're going to sort the left half. So the left half is everything from 0 up to the midpoint, and sort that into the left half of the output. Then we're going to sort the right half. So the right half starts at mid. It has size minus mid things in it there, and then copy that into the right half of the output. Now, this loop here in the middle, this might not be completely obvious. Like, why do we need this here? So the idea is I have my input, right? So my input is unsorted stuff. It's just like whatever, like that, right? After these first two recursive steps here, my output looks like this. It's left half sorted, right half sorted. But merge needs the input to look like that. So this loop here just copies that back into the input so that my input looks like what it needs to look like to go into the merge function there. So then we merge it, that transfers it back into the output array and puts it whole thing in ascending order there, like that. This merge here, right, this takes O of n time. So the runtime of this here for this recursion is going to be the size of the recursive tree times the sort of O of n that we have in here. But this n in here, this size in here, is going to get smaller and smaller because we're doing size divided by 2 on the way down here. We'll draw a picture of this here that should make the runtime clear here. But first, let's like sort of conceptually think about how this looks, right? So on the way down, we're sort of splitting and then splitting and then splitting again and so forth until eventually we hit those base cases there, like that, right? We're not really doing anything here. We're not physically splitting the arrays up. We're just kind of like figuring out like where the split points should be. And then on the way back up, we're merging by sort of like reversing our steps here. So we merge, and then we merge, and then we merge again there, like that, until we've rebuilt the entire array there, like that. So like you can visualize it like this. We're starting out with size many things, however many things we sort of have there. So we split that in half, and now we have 2 things of size over 2. They're still in the same array, right? Like this isn't like 2 separate arrays here. It's just 2 halves of the array. So all I'm really doing is keeping track of like where's the beginning and end of the 2 halves there. Then we split those in half again, so now we have 4 things of size over 4. And you just keep doing that until eventually you get down to size 1. So this takes me log of n many sort of like levels of stuff here to get down to the point where my size is 1 there. 1 is my base case, so that's where I'm doing that sort of copy from the input into the output there. And then I can start merging. So I pair things off and I merge them up to get things of size 2. And then I get size 4, size equals 4, and then eventually I rebuild everything back up to the original size. That takes me another log of n steps to get up there. So my total height over the whole thing is like, 2 times log of n, but in big O terms, that's still log of n. And then going horizontally here, each level of this merge going that way takes O of n time here. So I spend like O of n time here doing these merges, and then I spend O of n time doing the next level of merges, and so forth all the way up here. So the total runtime of this is the 2 times the log of n on the vertical side here, times the O of n on the horizontal side there, for a total of n times the log of n there. So let's try it out. Let's run this on this sequence of size equals 8 here. 8 is, of course, like a nice size to do a merge sort on because we can split, and never have like an unbalanced split there like that. So we start out with size equals 8, split that in half. And again, like these are still technically part of the same array, right? All I'm doing is sort of visually showing where the split points are there. Split again. Split again. Now we hit size equals 1. That's our base case here. So then we're going to start merging things back together. So I'm going to merge 4 and 3, -5 and 0, 9 and 6, and 7 and 2. So when I merge 4 and 3, right, that flips them around, puts the 3 first and the 4 second. When I merge -5 and 0, that doesn't do anything. When I merge 9 and 6, that flips those. When I merge 2 and 7, that flips those. Now notice what I have, right? I have this, these are 2 halves of a sequence, these are 2 halves of a sequence. I have ascending, 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 ascending. So I can merge these. So that merges 3, 4, and -5, 0, and 6, 9, and 2, 7. Right? And now again, like these are still part of the same array here, so I have ascending and ascending. I can merge those, and I get the final array here like this. So now my entire array is sorted in ascending order there like that. So it took me log of n levels to sort of get down to the base case, right? And then it takes me another log of n levels to rebuild it back up to the original size there like that. A fun variation on merge sort is what's called a bitonic merge sort here. So in a bitonic merge sort, we still have our 2 halves, but the left half is sorted in ascending order, and the right half is sorted in descending order. This actually ends up simplifying the loop inside of merge if you kind of work it all out there like that. But it adds a little extra wrinkle to it because sometimes we need the output of merge to be ascending, and sometimes we need it to be descending. Assignment 3 will ask you to do a different variation on merge sort, which is merge sort on singly linked lists here. You might think that that would like blow up our big O runtime because it's like, well, we can't just jump to the middle of the array there, but actually the runtime doesn't change. We're still running in n log of n time here when we do it on a linked list. In fact, there's actually a few like advantages to doing a merge sort on a linked list there. So merge sort is our sort of first sub n squared sorting algorithm. It's provably optimal, runs in n log of n time, but its main downside is that it requires an extra O of n memory there. We have our input array and our output array there like that. So if you want to, you can jump into the assignment 3 video or the assignment 3 prompt there and sort of see what it's like to do a merge sort on a linked list. That's it for now.